And I'd like to welcome everyone. This is the first talk in the spring 2023 CDY session. And as you know, we have these talks once every other Wednesday. So please join. And today's session will be kicked off by Frank Rieger, who will talk about particle acceleration and shearing flows. The topics that we've selected for this semester is basically a continuation of our fall series on multi-messengers. And for the next few months, we will focus on cosmic rays and gamma rays. So Frank is an expert in this field. Of course, he doesn't need an introduction, but just me give a quick one. He's currently at the Institute of Theoretical Physics and Max Planck Institute at Heidelberg. And he has worked on this field for a long time. He had his PhD from the University of Göttingen in Germany and has held several positions at the University of Würzburg and University College Dublin as well. He's an expert on particle acceleration processes in astrophysical jets and non-thermal processes in black hole jet magnetospheres. So without much ado, let's welcome Frank and get started. And as a reminder, Frank, we will do something like 50 minutes for your talk, and then we will follow with questions, and people should feel free to use the chat feature. And then what we do generally in the last 25-30 minutes is just have a general discussion on any topic related. It can be a little bit broader, and hopefully everyone can participate. And another reminder is that we will be recording the session for our YouTube archives. So please mute yourself if you're not speaking. So Frank, get started, please.
So thank you very much, Reshmi, for this kind introduction. Let me share my screen. So you can see it?
Yes, it's perfect.
Okay. Give me a moment. Okay. So it's a great pleasure and honor to give a talk in this series, which I really appreciate. I'll have changed the title a bit to particle acceleration in relativistic shearing flow. And this already has a take-home message that particle acceleration and shearing flow is essentially only efficient in relativistic flows. To give you an outline of my talk, I will give you an astrophysical motivation, kind of describing an exemplary context where shear acceleration could be operating. And this has given momentum over the last few years in this kind of analysis. So these are large-scale jets in HN. I will kind of explain that the origin of extended high energy emission that we see from those sources demands a very efficient acceleration mechanism that operates all along the jet. And one example could be a shear type particle acceleration mechanism. I will try to convince you that shear flows are kind of naturally expected in HN type environment. And then I will focus on really shear type particle acceleration, on a stochastic Fermi type particle acceleration mechanism. I will explain the basic idea. And then we are particularly interested in the acceleration time scale and what kind of power laws we might expect by this type of mechanism. And then we will kind of put that back in context and think about how can we model these kind of extended high energy emission that we see and kind of expect in HN by a shear type particle acceleration mechanism. And we will use information that we have here to think about, well, if we can accelerate efficiently electrons, maybe we can also efficiently accelerate cosmic rays. So we close with a discussion of potential scenarios for ultra high energy cosmic ray acceleration. Now, the context is large-scale jet in HNs. So by that, I mean relativistic flows, right? Supersonic flows that kind of crash into the ambient environment, create a hotspot, excited backflow, and where we talk about flow Lorentz factors of, say, mildly relativistic 1.5 up to 10 in the bulk flow speed of the jet. And the typical example, at least in the radio, a nice example is Cygnus A, right, where you see this would be the core, the black hole, you pass the scale jet, where very often you think gamma ray emission in HN emerges, and then all along of a 50 kiloparsecs, and you see it creates the hotspot and excites the lobe type radio emission. Now those jets appear laminar. in some sense, at least if you look at it, though the fluid Reynolds number would be very high. So you would normally expect this type of jets to be highly turbulent, and though they are still such that they maintain distances up to 50 kiloparsecs in this type of sources. Now, one of the interesting questions, for at least from a gamma ray and the high energy perspective, was the realization. Now what I showed you was signals A in radio. We know that those sources, large scale jets, are visible in radio. This is the second nearest HGN, M87. But it also shows in the optical HSD high energy emission, optical emission all along the jet, and it even shows high energy emission, X-ray emission along the kiloparsec scale jet. This came as a surprise and initially kind of created a debate of what is the cause of the X-ray emission in this type of large scale jet. And say the contenders in this field were synchrotron X-ray emission, but that would mean that you would need very energetic electrons. Or the alternative was that it inverse Compton upscattering of the CMB by radio emitting electrons. But that would kind of mean that you would need highly relativistic flow speeds to make this efficient. Now the debate kind of has moved a bit. There has been development in the field, and one is that we kind of see in more and more sources that the X-ray emission most likely is electron synchrotron emission. I show you one example of this type of sources. So what we did is, now we can extract. Wait a moment. So what we can do is we can do the full Chandra analysis. So not only a flux point, but take all data and extract the spectra. And what you see is that this spectra is not compatible with this type of power law, something you would expect in an inverse Compton CMB scenario. So this kind of gives you a kind of a good argument of saying this is most likely synchrotron emission by a broken power law particle distribution, but it would mean that you need electrons up to 10 to the 8, and those electrons would have a very short cooling time scales, the 1 over gamma, resulting in a cooling length which is much smaller than the kiloparsec scales you are observing. So in order to see extended distributed X-ray emission all along the jet, you would need a mechanism that continuously operates all along the jet, not only localized in region which you may associate perhaps with shock type particle acceleration. So this kind of was an indirect evidence. There is now much more clear evidence by the observation of gamma ray emission from the kiloparsec scale of Cena. So the nearest HM at 4 megaparsecs, you again see a kind of a kiloparsec scale jet of 4 kiloparsecs here in X-ray and in radio. And what Hess has observed is and has seen is extended gamma ray emission along the kiloparsec scale jet of Cena. What does it mean? You can now disentangle the electron distribution, because what you see in gamma rays is the upscattering of the dust emission and indeed of the CMB now. But the CMB now is upscattered by energetic X-ray emitting electrons up to the TV, and as well the dust emission. So what you can now infer is that you kind of verify the X-ray electron synchrotron interpretation. You indeed have 10 to the 8 electrons all along the kiloparsec scale jet of Centaurus A. And if you try to model it, you can nicely fit. So this is the kiloparsec scale emission that you see, HSD and X-ray Chandra. This is the hash measurement. This would be the core emission. We are now talking about the kiloparsec scale jet. And so now you can nicely fit with synchrotron X-ray emission and inverse Compton upscattering by dust, the full SED that you see. And for those working in the field, you even are able now to account for the spectral hardening that came as a surprise initially in the core emission of Centaurus A, because there's a feature coming up here from the kiloparsec scale jet. Now, if this is the case, if you believe there are electrons of 10 to the 8 along the kiloparsec scale jet of Cena, and that there's an efficient mechanism that kind of provides those continuously, we could also speculate, start thinking about and say, maybe large scale jet are also playing a role in the acceleration of ultra high energy cosmic rays, right? We would think about those particles above 10 to the 18 that we see. And if you look into the Hiller's diagram, right, so the radiant galaxies jet, those would be, well, privileged possible candidates of doing that. So at least those are the candidates you would be focusing on. And now you have an example and kind of more motivation to have a closer look into. Now, this as a way of introduction and putting the context. How can we now accelerate electrons to 10 to the 8 and keep them energized at that level on those distances? And I will talk about a possible scenario, which is a Fermi type mechanism. By that, I mean a repeated mechanism where you're repeatedly building up your particle distribution. You energize your particle by repeated scattering mechanism. You know Fermi type particle acceleration, first order in the case of shock. We have the classical second order Fermi acceleration by random motion of scattering centers, and shear is a variation of that, but it draws on the systematic velocity difference in the background flow. So let me explain what do I mean, or what do we mean when we are talking about shearing flows. So far we have been talking about a flow that has a uniform flow velocity, right? Everything is uniform as it propagates outwards along the jet. A shear flow would be a flow where you say, well, this certainly is a first order simplification. Most likely the flow has a velocity shear, so a flow profile that changes along the x coordinate. If you think that to be the jet radius, right, that there may be, for example, a spine in a shear layer and so on. So the jet itself has a lateral velocity change. This is where the velocity profile is smooth. You would talk about a gradual shear flow. If you say, I'm considering a flow profile of this type, a non-gradual, a velocity jump, then this would a kind of this type of feature. I will talk about both of them during my talks. You would associate over the years perhaps name with those like Berezko and Grimsky, who did early work on this, Earl, Jacobi, Morfield in the relativistic regime web, and I myself with Peter did work on that over the years as well. Non-gradual shear, Jacobi, Morfield worked on those, Ostrovsky, Kimura, Caprioli, and so on. I will kind of mention those as I go ahead. Now, you could ask yourself, okay, this is nice. There may be a mechanism, so why shall I think of? And it has some intuitive appeal of thinking that the flow is more complex. Now, have I, in the context of HN, more solid reasons, better reasons to think about it? So I mentioned only three kind of evidences. You would expect that the general mechanism of forming a jet is a black hole-driven, ergospheric-driven jet that is surrounded by a slower driven, disk-driven Blandford-Payne outflow. That would naturally mean that by the onset of the already very close to the black hole, you have a flow stratification, a fast, a spine and a slower disk-driven wind. And as the jet propagates, then you have all type of instabilities mixing both within the ambient medium between those two flow interfaces. Kelvin-Helmholtz, which I will talk later on, you have the mixing between those, you have a layer formation. You kind of naturally generate a velocity layer in this type of environment. You could ask yourself and say, well, do I also have some observational evidences that may be interpreted in this kind of context? Well, those that have been done, for example, are the limb brightening, the different kind of features across the jet that you see, polarization signatures as you go across the jet. And one example, for example, is M87, where you can now laterally resolve. So laterally resolve the flow motion very close, already so 200 Schwarzschild radius, very close to the black hole. You can follow components as they move outwards, and you can kind of identify flow velocity profiles. And those would indicate that what you see is both a slow and a fast component already very close to the black hole. You see similar indications in the case of Sen-A. So there is kind of a context where you say, okay, let's continue and think about what we can do. So when I talked about the Fermi type particle acceleration, what do I mean by that? I mean, Fermi type particle acceleration, if you remember, was of a kinematic effect that results from scattering, and in the Fermi picture from a magnetized cloud that has some velocity. And so you have a particle entering and crashing on this cloud, getting scattered, elastically scattered, and leaving the cloud with some scattered velocity, some final velocity. In the Fermi picture, you have this repeated scattering. There are more clouds, or the particle scatters all the time, right? It's like a ping pong game and increases with time its energy. The ingredients in the Fermi picture is such that you say the scattering is such that the momentum magnitude, the energy is conserved, but the particle direction is randomized. So it enters and then it leaves the cloud at some random direction. If you kind of figure out what is the classical energy change in an elastic scattering event, well, it is simply given by this expression of saying, so this is final energy, initial energy, and this is proportional to the bulk Lorentz, or to the Lorentz factor of your scattering centers, so the gamma S, times the initial energy of your particles, times the speed of the scattering center square, times the scalar product between, say, momentum direction of your particle and velocity direction of your scattering cloud. And if you try to look at that, what does it mean? So if you have a head-on collision, right? So where the scalar product is negative, this term is positive, and you have an energy gain. If you have a following collision where the scalar product is positive, this is negative, and you have an energy loss. So in principle, this type of mechanism is you gain energy in a head-on collision, you lose energy in a following collision. But there's a higher probability for head-on collision. This is why you increase substantially with time your energy. So stochastic acceleration is something where you say, okay, this is for one cloud and for one particle. Now I have to average over an isotropic particle distribution if I want to know what my particle distribution does. So this is the cosine averaged, it ends up to 0. So you end up with an average energy gain, which is of order second order in the scattering center speed, right? Which is why this called of classical Fermi type acceleration is called second, or is often referred to as second order Fermi acceleration. So the energy change is proportional to the second order of the scattering center speed times the energy, right, of the particle. Because the particle is relativistic, the momentum is energy divided by c. Shock is a situation where you have spatial diffusion and where you kind of create an environment where you have only head-on collisions. So the particle crossing the shock sees the other side approaching always. So you have a head-on collision, and you are able to keep this term. Okay, a head-on collision. So you have a first order term. So energy change is proportional to first order of the scattering center or the shock speed in this picture times the energy of the particle. Now, if you look with that kind of picture on non-gradual shear acceleration, then this can as well be viewed as a second order stochastic Fermi type process, where the average gain per cycle is, right? So what you have here, this was this velocity jump that I showed you before, non-gradual shear. You have a particle that moves across this velocity jump. And what it does is, in a full cycle, going up, going down here, it is of a second order Fermi type. That means the energy change is proportional to flow speed to the power of 2 times the energy. Flow speed is the relative speed between this one and this one. So this is a kind of second order Fermi type mechanism, and it applies provided, and this is kind of good keep in mind, provided the particle mean free path is such indeed that you can assemble the full velocity jump as a particle moves across it. Then you can associate an acceleration timescale with it. What is an acceleration timescale? Acceleration timescale is energy over rate of energy change. Okay, energy, rate of energy change I have. The dE is the delta E. Okay, I can plug in. And the time over which I change, which ends up in the denominator, is the cycle time. So typically I have an acceleration time which is proportional to the particle mean free path, the ability to cross the flow velocity jump. Okay, now gradual shear is now a picture which is slightly different. That the flow profile is, as I showed you before, of the smooth type profile. Again, you have a particle moving along across the shear and kind of experience the difference in the flow that you have. So again, this is a kind of second order Fermi type process, a stochastic process, where the energy gain is second order to the relevant effective speed that is experienced. Now you can ask yourself, what is the relevant flow speed difference that I experience? Well, it's simply the gradient in the flow, right? That is available to me, and the times the particle mean free path, the way the length I go across the flow. So this is the gradient of the flow times the particle mean free path. Okay, if you plug that in, you simply write it in, then this effective velocity is the gradient to the power of 2 times lambda to the power of 2, where lambda is the particle mean free path. Now, again, if you ask yourself, what is the acceleration timescale, as we just had, is the energy divided by rate of energy change. Again, we have the delta E expressed here. And the time that is available to us is simply particle mean free path divided by c, right? Because this is how you relate the particle mean free path to the mean scattering time tau. Okay, so if you plug that in, you have here the lambda dependence, but this one brings a lambda square dependence. Okay, so you have lambda divided by lambda square, and you end up with an acceleration time scale, which now, in contrast to what I just described you before, to classical second order Fermi or non-gradual shear acceleration, is inversely proportional to the particle mean free path. Now, what this means is it sounds at the first moment a bit unusual, because it means that the higher and the more energetic the particle becomes, the easier it gets to accelerate it. And the rationale, the reason behind that is that as the particle mean free path gets larger, you have a higher probability to sample a higher flow speed difference. And this is what goes in here. So the 1 over lambda dependence is kind of a unique feature for this gradual shear type particle acceleration. What does it imply? If you look at it, it means, okay, in order to get it efficiently started, imagine lambda would be very small, then acceleration timescale would be enormously high. Okay, so you would need some seed from another acceleration mechanism. Think of a shock type acceleration mechanism. Think of classical second order Fermi acceleration that provides seeds until you cross a threshold at which the 1 over lambda dependence becomes relevant and shear becomes faster than, say, the other acceleration mechanism you have been considering. It also implies, and as we will look at that it seems to be easier for protons have a much larger mean free path, right? Heavy nuclei, cosmic rays are much easier to accelerate compared to electrons, for example. Now this has a long history. So this goes back to Barretsko and Grimsky, and as I told you before, to Earl in the relativistic regime, to Webb. And I have added conceptual clarification and application in that context as well. But this is a kind of Fermi type mechanism which is of second order, but has this interesting appearance of an acceleration time scale inversely to the particle mean free path. Now you can convince yourself, okay, what is going on here? And look at it and say, okay, what I can do is I can calculate what is called the Fokker-Planck coefficient. So I can think about how does the momentum or the energy change with time, and how does the dispersion, the delta P, to the square change with time. And you can do that in a non-relativistic shear by saying, okay, what I do is, if I move across the shear flow, my momentum of my particle changes. If I have initially here a momentum P1 and I move across the flow, then I have a momentum P1 times, if I assume a Galilean transformation, well, mass times the delta U that I experience. And the delta U that I experience is just the gradient in the flow times the length over which I can go across this flow. And then you take the magnitude and you average over an isotropic particle distribution, and you end up with the Fokker-Planck coefficients. So you have a delta P, which is, as we just had before, proportional to the gradient to the power of 2. And because the delta T is here and brings a tau here, to the tau to the power of 2, or the lambda to the power of 2. And you have for the dispersion a similar relation of depending on the gradient to the power of 2. You can convince yourself, those working in the field, that detailed balance is satisfied. And that means that the Fokker-Planck equation that you write down reduces to a momentum diffusion equation. Okay, so that means if you want to describe shear particle acceleration, it is a stochastic acceleration process. It can be cast in a momentum diffusion equation of this type of form, where the diffusion coefficient, right, is now dependent on the gradient to the power 2 and times the particle mean free path. Okay. Now you can ask yourself, so what does this mean? You talk about how can I visualize that? So this is the diffusion equation, and you now take the derivative. So what you end up with is, right, if you take the derivative, you have one term, the delta F over delta P. So this one and this one, you have a second derivative, delta over delta P to the power of 2. Okay. This first term describes the change in mean energy. And this one, like if you remember in a Brownian motion, the broadening of the distribution. So if you take an example and say, look, I assume an instantaneous injection at time tau 0 with some momentum, and I assume a momentum scaling for the particle with a constant one. So what happens here is, in this type of process, you inject a narrow distribution, okay? And as time progresses, the distribution broadens with time. Okay, no surprise. This is a diffusion process, and it kind of mimics that what is behind from the kinetic picture is that there are many frequent scatterings where you have head-on collisions that would lead to ending up here, but you also have a probability for following collisions that would lead up here. Okay. But because, as I told you, there's a higher probability for head-on collision, and in the case of shear, this applies as well. This means if you look for the energy distribution of the particle, so say p squared times dnp, you see that the p kind of shifts with time to higher energy. So you have a mean energy increase with time. Okay, this is kind of the stochastic process. Now, this was early on realized. So what was done is that one can solve the non-relativistic version of the gradual shear particle diffusion equation, right? Like what Beretsko did in the 82s. And you end up with a local power law formation. So at highest energy, the power law index, so this is particle distribution, so p squared times the phase space distribution, and it says a simple relation is -1 plus alpha, where alpha is now say how you parameterize the scaling of the scattering time or the particle mean free path. So if you would assume Kolmogorov, so alpha would be 1/3. If you would be Bohm time, so gyro dependent, alpha would be 1-ish. Okay, and then you would have a power law -2. If you would have, if that sounds particularly exciting to you, then this would be -2 in that type of for Bohm type acceleration. You can see that now. This is what I did here is a time-dependent solution of the Fokker-Planck equation, and here now in logarithmic log representation, such that you see here the power law already forming, right? You have the same shape here in the power law, and it's actually obeying this kind of expression. Now, this was this was the initial idea that you say, okay, I'll generate particle distributions, and depending on the momentum index, I know what kind of distribution I have. Now, if you think closer, this will not be as simple, because what happens then is this mechanism of gaining energy is intimately related to a particle moving across a flow. But that means, in principle, I'm not allowed to neglect and ignore the spatial transport of the particle. So the diffusion process of the particles across the flow. I have to watch out what happens. So I know now how the particles gains energy. I know how in the momentum space it changes its energy, but I would want to know how in real space the particle distribution changes, and that could impact. It could lead to an escape of the particle, and that is one of the examples. I showed 2 slides now for the particle transport theory, and then we go back to an application and it becomes easier. But behind that now is the following. What you do is when you do try to understand the particle transport, you start from the Boltzmann equation. Okay, you start from a Boltzmann for partial differential equation that describes the behavior for a thermodynamic system out of equilibrium, right? And you add a collision term that brings things back. And it's practice in this kind of approach to evaluate, to use a mixed frame particle transport equation. What does it mean? You kind of explore time and space in the lab system, but for evaluation of the momentum, you move into the co-moving frame. And behind that is, as I told you before in the Fermi picture, that in the frame of the scattering center, the scattering is elastic. So you have a very easy way of describing collision and scattering in that frame. So that means you have a mixed frame particle transport equation. You again apply a Galilean transformation, and you assume the scattering ensures that you have an isotropic part and a small anisotropic part. And then you end up with a classical transformation, the time derivative. This is an advective term, okay? This is adiabatic energy change, the P over the third over the P, and this is spatial diffusion. And because we are kind of having this mixed frame transport equation, we have inertial terms, because our system is no longer inertial systems. So we have an accelerated system, and all these terms with AI are related to this one. And we have a shear term, okay? So if you now look into a steady shear flow, like as we had before, of say that the flow is in the z direction, but varies along the x coordinate. You can convince yourself that adiabatic and the inertial term vanish is equal to 0. And that means that you lose all those terms, this one, this one, this one. And that the space-independent part of the particle transport equation, right? The space-independent, this is space-dependent, this is advective, spatial diffusion, is indeed equivalent to the shear diffusion equation. What we had before, right? This is the diffusion equation. But we have, in principle, for the full particle transport, spatial transport as well. Because we will look into relativistic, we in principle even have to go a step further and say now we have to make everything relativistic and make sure that we are applicable and everything works for relativistic flows. And you end up with the relativistic particle transport equation that goes back to the generalization by Webb. Again, in that case, for a steady shear flow, right, the one that goes out and changes along the radial coordinate, for example, the fluid 4 acceleration, which is the dot term here and the dot term here, vanishes, and the fluid 4 divergence vanishes as well. So again, you end up, this is time, right? All these terms are gone, and you end up with a spatial term, which has the matrix and the diffusion coefficient and so on, and the relativistic shear expression term that we are now familiar, right? This is the delta over delta P times this expression, the diffusion equation that describes energy change in a gradual shear flow. If you want to get a closer look into that, let me recommend a review that I have written on that, and that kind of explains that again step by step, and also focus on, because if you talk about shear flows, there have been different kind of approaches and different contexts in which one can view that. One is the microscopic shear flows, so kinetic physics, peak simulations, and you would associate, for example, those names with it, Lorentz or Edison Liang and so on. I will mention one at the end of my talk. but also large-scale turbulence. And Andre, for example, has worked on that, and you could look on that. And there is part on this where I describe that and comment on that. So I recommend that to you as an introduction and overview. Okay, now what we kind of learned, hopefully, is the gradual shear can be cast, the energy change can be cast into a momentum diffusion equation, okay? But we also realize, but there is spatial transport, somehow we need to address that. And the easiest way to address that is to say, okay, let's start with the diffusion equation, but then add some escape term, some average leaky box type escape term. There's a finite probability for the particle to escape, and then try to solve and look what happens. And if you do that, you again find power law solutions. Okay, so the phase-space distribution is minus S. If you think of the particle distribution, it's minus S plus 2. But now what I have shown here is that the power law index, this S that you get, depends on the flow speed that is available to you. The flow speed, think of the maximum in a linear shear, so the highest spine speed that is available to you. Okay, so that you only get, in this case, this is alpha equals 0, so that you get to the tree, to the one that I showed you before by Beretsko and Grimsky and so on, that you say you only get to that in principle for ultra relativistic speeds. As you go to lower speeds, right, the momentum index becomes softer and softer and softer and softer. And if you would go to non-relativistic speed, you would be super soft. It would be non-efficient. So the take-home message of that out of would be of saying shear acceleration. So two things. Shear acceleration will require relativistic speed, mildly relativistic, highly relativistic speeds to be efficient. And there is no longer a unique power law index, but it depends on the flow speed that is available to you. If you talk about different large-scale jets, and if you know that they would have different speeds, say from the radio and so on, you kind of expect that they have different power law indices if shear applies, okay? Now, this is what we kind of did is try to go a step further and look into and say, okay, put that back into the large scale jet that we were kind of looking in my introduction. What does radiative loss acceleration do if we incorporate now synchrotron losses? Okay, we start with the diffusion equation, so the Fokker-Planck equation. We add stochastic second order Fermi acceleration, the classical one. We add gradual shear. We add synchrotron, and we add escape, and we consider a cylindrical jet. Okay, so there are two cases. One is where we say ignore escape, but keep stochastic second order Fermi acceleration. Inject monoenergetically your particle. Then what happens is the following. Classical second order acceleration will initially be much faster than shear acceleration. So we'll start shaping, and this is gamma squared times ng, start shaping the part distribution until at some stage you cross the, as I told you, the 1 over lambda dependence for gradual shear. You cross the threshold where gradual shear becomes more important. And you kind of change the power law indices, and then you have a pileup because you ignore escape. Okay, so the take-home message of that here is you kind of naturally generate a multi-component power law particle distribution. You no longer don't need the cooling break or whatever, because this kind of produces natural and multi-component particle distribution, where you change the power law index going from one mechanism to the other. There's one mechanism providing the seed for the other. Now, if you look into and say, let's focus on the steady state, ignore stochastic. So let's talk about this part, but include escape. Okay, if you include escape, then what happens, as I told you before, so the spatial transport means you would need high speeds for having hard spectra. If you would have low speeds, you would have soft spectra. Okay, so if you want to as take-home message, you are able, you can go to 10 to the 8 for the numbers that we now use that seem applicable to, for example, Centaurus A and for M87. You can go and keep 10 to the 8 electrons energized. You would have a multi-component particle distribution, and the way you treat the escape, the spatial transport, has implication on the softness of the spectrum that you see. Okay, this now you can put back and say, okay, let's go back to Centaurus A. And this is one example where you say, okay, this part, take this part to be generated by shock type particle acceleration, the -2-ish type. You can keep those particles energized for quite a long time along the jet, even if they have initially injected quite early on. Okay, they don't have as high energy. And then say they provide a seed for a shear type particle acceleration mechanism, and it's this one, the -3.9. This is the particle distribution that is needed, a strange one, but a soft one that is needed. And you kind of explore what would that require if it's done by a gradual shear type particle acceleration. Okay. You assume Kolmogorov type turbulence, so you kind of fix the particle mean free path as dependent on the momentum or Lorentz factor of the particle to the power 1/3, and you look into a quasi-linear shear. And then you can reproduce those by having a shear width of 100 parsecs in Centaurus A, which is feasible. You have a magnetic field which is close to the equipartition value, which is feasible as well. And you have a maximum speed in the jet, which is of the order of 0.7, which is a bit higher than what you see in the radio, but it's still feasible. So you can play the game and say, okay, maybe this indeed is electron acceleration up to 10 to the 8 that I expect from gradual shear, and I have a constraint on the parameter that I need to let this working. I'm stressing that because in principle, if you now talk about ultra-high energy cosmic ray, if you have information, say spectral information from high energy, from X-ray and from gamma ray, you have constraints on this part, and you are no longer really completely free to do with your ultra energy rays whatever you want to do, right? So there's a way of kind of connecting what you see at X-rays energy, for example, and at ultra high energy cosmic ray energies. So you would want to go a step further and look in and say, what shall I expect? So at the moment, I was talking about the shear width, the 100 parsec and so on. What shall I in principle expect? Let me inform. And so what we did is relativistic MHD simulation using Pluto, looking for jet velocities between 0.6 and 0.99, and examine what would happen if you have a jet spine propagating into a hot cocoon environment. In the case of a kinetically dominated jet, right? So sigma is between 0.02 and 0.02. And you can look into and say what will happen is that you will excite Kelvin-Helmholtz instabilities. And you can look in how do they shape the velocity. So the difference that I see, they generate kind of a sheet layer. So this is the spine, this is the cocoon, and you will see that they generate a sheet, and you can kind of look into what is the sheath width, the velocity profile that I may expect, and what is the turbulence that I generate by Kelvin-Helmholtz instabilities. And simply two outcomes of this is that what you see indeed is, so you start with a spine cocoon feature, and you see how Kelvin-Helmholtz instability kind of generates the sheet, right? You generate a sheet with time depending on, so this is kind of in the transition regime. This one and this one here, you can look into what is the e-folding time of the Kelvin-Helmholtz instability that you have. And this would be in the deep saturation regime. And so you can kind of relate what is the, say, the spine in the shear layer width. Okay, in the deep saturation regime, the layer is of the order of the jet spine width. Okay, so you have macroscopic layers, obviously of the order of the jet width that you are talking about, depending on the stage you are considering. And you can extract what kind of turbulence, so velocity turbulence and alphenic turbulence, do you see? Because as I told you, it depends on the scaling of the particle in free path. In that case, you see a kind of turbulence that is compatible or consistent with Kolmogorov type turbulence. So this kind of gives you an idea of saying, okay, if I have a kinetically dominated jet and I use numbers for a large scale jet, I should have macroscopic shear layers, and I may work initially with a Kolmogorov type turbulence and study that in more detail. In principle, you now also have an idea of the flow profile that you can use and kind of interpret for the particle distribution. And this kind of is a second step of saying, now what you can do is you go back to the full particle transport equation that I showed to you before. And again, a cylindrical geometry, and you do the full analysis. And it turns out, as I told you, that the index is fixed for ultra-relativistic flows. But for mildly relativistic flow speed, and this maybe is a take-home message as well, as you should have expected that you are sensitive to the gradient of the flow, okay? If the flow has a different profile, the flow gradient will look different. So you get slightly different momentum power law indices for the particle distribution. So at mildly relativistic flow speeds, the power law index gets softer and you become sensitive to the flow profile. Okay, this is shown here where I kind of explore different, going from a linear decreasing flow profile to a power law profile in a Gaussian type profile, right? Gaussian type profile. And you can then say, okay, but from the radio, I kind of have this regime 0.7 for Centaurus A. I need for my spectral fitting an index in this regime. So what type of flow profiles would be best or consistent in this simple approach with the requirements I need? So you have a way of linking the flow profile to the power law index. Now, this was kinetically dominated. I think I have 5 or 10 minutes. I have 5 10 minutes. Okay, hopefully. Just for a quick interlude. So these were kinetically dominated flows. You can now look also for highly magnetized shear flows. And this would only say apply for, in my opinion, for very close to the black hole, the origin of the jet. And this was done by a nice work by Lorenzo. 2D peak, a highly magnetized electron-positron jet, but sigma of 100 now, super high, propagating in a weakly magnetized ambient plasma, focusing now on wider shear layers, right? Still on plasma, on 10-ish of plasma skin depth. So what you learn here now is, in my opinion, you learn something conceptually, you gain physical understanding. Still keep in mind that this is 10 to the 10 orders different from the astrophysical system we are discussing. But still, so what happens here is this is kind of a 2D peak, a flow that goes in that direction as a magnetic field, and you see Kelvin-Helmholtz instability developing. So after 10 to the 4, so this is 80 plasma frequency, inverse of the plasma frequency. This is 10 to the 4 inverse of the plasma frequency. You start with a parallel field. And you see that Kelvin-Helmholtz starts twisting the magnetic field, generating a magnetic field in that direction. You see this type of plasmoids that get ejected, and you see it in early stage even much more significant. So what happens is you see a shear layer getting formed, similar to what we kind of had before, right? The width of the shear layer of the order of the spine width. You have these plasmoids in which reconnection most likely takes place, and what they see is reconnection in this type of plasmoid type features that you have here, of the order of the in-plane magnetization, the sigma that they use, which is 10-ish, so they get 30 in maximum energy for the electrons. And if you look at this, and this is why I highlighted that, this is happening, actually the regime where you see the energy gain, right, is actually the shear layer, okay? This is the shear layer where you see this type of happening. And in that, this is kind of what they explored further is, this is providing the seed for further shear acceleration across this type of flow. But again, remember, this is now a highly magnetized flow, so different from what I have been explaining, but it conceptually providing an example of a mechanism that could also provide seeds in a highly magnetized flows. Okay, let me go for 5 minutes on ultra high energy acceleration. Now put that what we have learned in large scale HEN jet. And the picture would be that you say, okay, maybe the simplest is to say, I have a pickup of galactic type of cosmic rays. I have galactic cosmic rays surrounding my my propagating jet. They enter the cocoon, they enter the shear layer, and they get further boosted up by shear type particle acceleration to high energy. Now, if you do that, you can, in a Hillas type approach, say, okay, what would be needed? You would need to confine the particles laterally in your shear layer. If you talk about gradually shear in a large scale jet that is mildly relativistic, you would convince yourself you need to beat the losses, the synchrotron losses that would be operating in any case. And you need to operate within the system lifetime, the time that is available until the particle gets ejected out of the large scale jet. Okay, if you do that, you end up with a Hillas type of plot. This is the magnetic field, this is the width of the shear layer. And this would be the allowed region in which your parameter space would allow you to accelerate protons to 10 to the 18th. The lower limit would be given by confinement. This one would be given by synchrotron losses, and the dynamical is less relevant. So if you think about, you want to go to 10 to the 18, and you take a 10 to the minus 4 Gauss magnetic field, then something like, say, a 10-ish shear width of a few tens of parsecs is working out. Something like you would expect in the case of Centaurus A, something what you would expect from characterizing the shear flow profiles by Kelvin-Helmholtz. Okay, so from that point of view, you would say, okay, for the parameter space that are now protons, I can 10 to the 18 should be achievable for relatively plausible parameters. You will get an escaping cosmic ray spectrum that is hard depending on the speed. If you ask yourself, but okay, could I perhaps go to 10 to the 20? Then this is what happens. So you would shift all those lines up to higher and those to lower, and only that regime would be allowed for protons going to 10 to the 20. So you would already be at extreme numbers. So my conclusion out of this is proton acceleration up to 10 to the 20 in mild relativistic flows, well, appears quite restricted, if not really less plausible. At the moment, this is not a problem, right? Because Auger would kind of point to a case that the composition at the highest energy is heavy. Again, this is a simplification that you don't treat the full particle transport as I told you before. But this was gradual shear. You can also follow up another scenario where you say, okay, remember, suppose I have a very narrow shear, which is the assumption here. It is a crucial assumption, but suppose something like that would happen. And you would kind of pick up galactic cosmic rays, and they would be able to cross and kind of extract the maximum flow difference. So a stationary cocoon and a fast flow speed. So non-gradual shear, and because this is a large-scale F1 type jet, so mildly relativistic. Gamma of a factor of that is available to you of 2-ish or something like that. So what Shimoke and Kota and collaborator did is look what happens. You can now kind of prescribe the turbulence, and so they prescribe the turbulence in here. They've prescribed turbulence in here, boom, and Kolmogorov, for example, here, and non-resonant at the highest energy, and looking for Monte Carlo transport and what happens. And then it turns out that you would tend up to produce very hard spectrum for the escaping cosmic rays. Not a surprise, but something that is seen now in the Monte Carlo simulations. You would have a maximum energy which is proportional to the charge number. So you end up with protons, if this is the intrinsic spectrum of ultra high energy cosmic rays, protons, for example, going to 10 to the 18th. And iron going up to, say, 10 to the 20, okay? And this break is coming from the change in the mean free path in the cocoon, right? You have a different description non-resonant scattering at the highest energy. And then you propagate that, and what you end up is you can reproduce the ultra-high energy cosmic ray spectrum now with a composition that is heavy, so at the highest energies, and protonic dominated at the lowest energies. You would still need a galactic contribution, right, to account for the full spectrum here. But what kind of this mechanism shows is the following. You could have large scale FR1 jet, so low power FR1 type jet, not the FR2 types strong power jet, in which you don't have many in the GCK horizon, actually. But for FR1, you have 10-ish, kind of, which you can work on. And they could operate and kind of lead to an accumulated spectrum that explains the Auger type spectrum that you see under the assumption that you have non-gradual shear particle acceleration operating. Now, the caveat, obviously, now, if you followed it, what I told you before, this assumed a minor, a thinnish shear layer, which most likely is not fully realistic, but we don't know yet what will happen if the shear is wider. It certainly will imply that the injection of the pickup cosmic ray that you have changes dramatically, right? Because they need to have an energy such as to cross that. But it shows you and gives you an idea of how FR1 type jets and non-gradual shear operation could make a difference in accounting for the highest energy ultra energy cosmic rays. Let me close, and this is the last one before I finish. So what I showed you before was an example where you look into non-gradual shear. You have an ad hoc description of the cocoon and the shear layer in the spine, but you can have full details on the turbulent particle transport because you prescribe what is the turbulence prescription in the cocoon and the shear and so on. You can follow a different approach and say, well, I want to have the shear layer jet propagation more consistent. So this is what Roston and Damioni did, is of saying, I do again Pluto propagation of a jet into the environment, and now for a powerful large scale jet, so of a 10-ish. Okay, and then I say again assume a recycling entrainment of galactic cosmic ray, and look what does it do. Now, if you have, as I told you before, non-gradual shear, if you go for the 10-ish type, okay, then remember non-gradual shear was gamma to the power of 2. You could have significant boosting of your pickup galactic cosmic ray. So in principle, only a few cycles would be sufficient to do it. And this is what Damioni has expressed, expressor shots of doing it. The strength now is that you now have kind of an understanding what is the magnetic field in the flow profile in a more consistent way. The weakness is that you lose, because of the resolution of your jet simulation, information on, say, on scales of 1/10 of the jet radius, which is the resolution of your simulation, which is the one where you think the particles are doing the stuff. And the way of treating or approaching that is to say, okay, I prescribe a diffusion process, and this is what I did. In the subgrid regime, I plug something in and look into it and say, if I would have many scatterings, if I would have Bohm diffusion, and they distinguish two cases. This now is a Bohm diffusion. I keep particles very close, scattering very often, experience the spine very often. And this one is where particle mean free path is free escape. Okay. So what you do is, if you increase the scattering, if you keep particles by your spatial diffusion close to the spine, obviously you get to much higher energy and to much harder spectrum, kind of what you would expect from a gradual shear type process. So the strength is that what it means now is your diffusion process defines again what kind of spectral shapes and energy gains are available to you. If you are interested in that, let me recommend a review that I have written recently, and where I kind of put those scenarios in context as well. Now, let me close and apologize for being late with the summary, and say, so particle acceleration, astrophysical shear flows, they need relativistic flows to work efficiently. By that, I mean to produce hard spectrum. If you think about for gradual and non-gradual shear acceleration, you need for the electrons an injection mechanism such that they can assemble enough of the shear or cross the non-gradual velocity jump. You need something like, for example, a shock type mechanism. But then they represent, in my opinion, a natural mechanism in type of HEN jets because they can kind of account for the origin of ultra-relativistic electrons and extended emission wherever I have a kind of shear and velocity distribution along the jet. They would lead me to the expectation of multiple power law formation distribution, right? That the distribution is now more complex because I see acceleration mechanism operating step by step. The spectral shape and the power law index will be indicative of the flow profile. And if you link those and those together, it would tell you that large-scale jet could also be possible ultra high energy cosmic ray accelerators. And this just for giving you the taste. There are lots of tasks ahead, as I explained to you. And let me close with that. And thank you for your attention.
Thanks, Frank, for pedagogically very clear and at the same time comprehensive description of this very interesting and process. So let's start discussion and let's start with questions. Let me see.
Maxim?
They are just, sorry, it's just, there are questions. Cannot see. I see one hand. It's Maxim. Okay, please, Maxim.
Hello. Thanks, Frank. I have like a comment and maybe it's like a question. As I see, you have like a very efficient acceleration for high Lorentz factor jet. And you have more efficient acceleration for high energy particles. So you, can you hear me?
I lost some. In my case, it was told unstable connection. Maybe not only on my side, but could you repeat, Maxim?
Okay, so like you have very efficient acceleration for high energies. You have very high energy, very efficient acceleration for high Lorentz factor jets, bulk. And do you think what your acceleration, in your case, you neglect by back reaction of particles on a flow so far? Am I right?
Yep. Yeah.
So, you, what I see here, like you should have a change of profile of flow, so what you will kill the acceleration. It's should be somehow similar results which described for GRBs by Piran and Derishev like a few years ago. And probably you will have formation of some kind of duty cycle when you have acceleration, deformation of profile and kill of acceleration. And you will have some kind of like a waves along the jet.
This may be possible. This indeed is a good point. So what this does is you can incorporate that in the particle transport equation by a viscous drag force. So if you would very efficiently accelerate particles in a huge number of those, you would take energy. You take the energy from the background flow, which means it formally corresponds to a viscous and therefore to a deceleration of the flow. So when I did that analyze in the context of the HEN jet, and this was for mild relativistic HEN jets, the viscous drag force was negligible small. But in principle, you're right. If I have an ultra-relativistic flow, and you could figure out what the energy you put into or is needed for cosmic rays, then you have a back reaction. This is not yet incorporated. As I told you, when I did this in some 10 years ago. This was for HN not relevant, but for this can now be quantified, right? Because in principle, you would now know what is the energy in ultra-high energy cosmic, for example, in ultra-high energy cosmic rays that is required in my kind of jet to explain the spectra, and then you would know it. Indeed, this is a good point. Yeah.
Well, is simply the extreme acceleration, right? It's just very just.
Sorry.
Felix, we're losing you. I think there's it's hard to hear what you're saying.
Okay. Sorry. Let me change my.
Meanwhile, maybe we can take a question from Richard.
No, but
okay, go ahead.
Is now okay?
Yes.
Yeah.
Okay, sorry. So, Frank, the question is this: can we reduce the non-gradual acceleration case to the gradual one? Just considering is a quite technical question.
It's technical in the sense that I would expect normally that I have a wide shear layer just from what we model. But then what happens is, so when I talked about this multiple power law formation, so indeed I would first need a seed mechanism that gets gradual shear started. But suppose I have a shear layer and my particle mean free path becomes larger than the shear layer, and I still have a substantial size of the velocity spine, then what I will in principle have, I will have a particle that once it has finished say gradual shear acceleration, it kind of experience non-gradual shear acceleration. So I have another kind of even further mechanism that pushes the particle, say, a factor of 10-ish or whatever, depending on the size of the shear layer to the spine, higher. So in my opinion, this is kind of a natural step mechanism. Once the particle gets, these cosmic rays get efficiently accelerated in a gradual shear layer, they may at the end experience non-gradual shear. Yeah.
Just results are so different. That is a bit interesting.
The results are different in the sense of spectral shapes. Because you would depend on the gradient in the flow for gradual shear, indeed. Yeah.
Yeah. Thanks. So, Rio.
Hi, Frank.
Hi, Rio.
It's great talk. Yeah, I have a question on this 3D simulation. This your new paper with Shearing, I guess that's one. The 3D simulation of the jet.
Yes.
You said this it could develop a shear profile of the jet, and in deep saturation case, it could goes to like I mean most of the jet can show this profile. I'm wondering, so how much is the time needed to develop this profile? I mean, from the beginning. How much time is needed?
How much time is needed? I showed you. This depends. Everything depends on the way of setup. But in that case, you have a feeling of, and say, okay, this is, say, for example, 60 R0 over C, right? And RC is 1 kilo is 0.1 kiloparsecs. So say on 6 kiloparsecs, if you go with this setup, you would have something like that. So you would expect that on the kiloparsec scale, which is where we were modeling here, it takes a while until you reach the E-folding time of Kelvin-Helmholtz instability, and then you start a transition regime and you start a steep saturation regime. And then you have this kind of feature, and it continues, right? Yeah. Does this explain your point?
Yes.
Okay.
Another question is that so with this profile, I mean, will it reach some how to say like stable state,
No.
or it will continue to develop?
This will continue.
Continue.
This is this is an azimuthal average flow velocity profile. So what you do is you kind of average it over the full azimuthal regime that is available to you. And then it would look like it is indeed a type of smoothish type of profile. But if you're stuck with that, this would kind of continue to develop with time, right? So you would widen with time the shear layer. Okay, so in principle, if you go to 100 kiloparsecs, right, this would be gone.
Yeah, but in this case, I mean, for this large scale jet, I guess because in the very center part in the core, it have a much faster speed than that.
Agreed. So this what I showed here depends on, again, depends on flow speeds. So we know that if the flow is relativistic, Kelvin-Helmholtz is tends to be suppressed. We know that if the flow is has longitudinal magnetic fields or is highly magnetized, it's more the King instability that becomes relevant. So this kind of is exploring a set of parameters, kind of looking for Centaurus A. If you, but this is, so it gives you an idea. But if you look for different parameters, you have to do the simulation anew, right? And indeed address those in question. Does this answer your case? I mean, if you say,
I was just
if I have a different sigma, if I have a different sigma, if I go to higher sigmas, the shear layer becomes narrower in principle.
Narrow, okay. But in that case, I mean, from some observation, we didn't see the jet with such a morphology. I mean, like the center is, I mean, usually for this large scale, we see like a cylinder-like or this conical-like, right? I mean, it becomes broader all side, but in this case, I would expect it's opposite, right? It's also like a conical jet, but I mean, farther it should be narrower because the central part is much faster than the other part. I mean, the layer part is the trailing behind this.
You would want to know the full jet propagation. Yes, I agreed. I agreed. That is okay. Then it depends obviously on the environment that will change along the jet. This is indeed. So this is a periodic box simulation. In principle, you can also do the full propagation, and this was done by Mukherjee, for example, of trying where you explore how does the jet propagate and what is needed for different types of sigma in jet power. Right? The jet power was 10 to the 43. This was kind of addressing here Sin A. It will make a difference. We know that high power jets propagate differently than low power jets, and so on. So this was more like, this is the first step in exploring, understanding, approaching what shall I expect if I plug in a regime that would be more suitable for Centaurus A. And I get kind of what
I understand. It should be conduct maybe more.
No, but this would be the best one. Again, you are limited then again by resolution issues, right? This is the full challenge that you have.
Okay. Yeah. Thank you very much.
Yeah, sure.
Yeah, thanks, Will. Richard.
Hi, Frank.
Hi, Richard.
Thanks for that intuitive talk. You know, I just want to ask a sort of question about the structure of the external medium in which the jet is flowing through, and whether entrained clouds would induce further shear layers, which may also enhance the acceleration, this mechanism, maybe at least at lower energies. And also clouds will be shocked as well, so they would potentially they'd have an internal shock, which may be a source of first order Fermi also to put into the flow. So, I mean, is that something which is totally not happening because the clouds just don't survive long enough, or what?
No, I don't know. There's a point in that you say what has been seen in, if you think about the Centaurus A jet, there are very tiny X-ray dots and points within the jets, many thousands that have been analyzed and that have been associated with stars, and you could say clouds, that are kind of having entered the jet. What it doesn't seem to do is, even on small scales, right, that the jet doesn't get disrupted by a cloud or a star entering. So what you could imagine, what it does is indeed, it triggers a local, for example, local shock. It triggers local turbulence. So this kind of, think of a cloud or a star entering the jet, it will kind of impact on the turbulence, the local turbulence description. So indeed, you could have then, say, a local shock type features that provides in that local area, if you think of a kiloparsec scale jet, local area some seed, and it provides some fresh input for turbulence. But because we are talking about now kiloparsec scale jet, we are talking about a width of the, say, of 100 parsecs. So this is, there are many in that volume, there are many clouds and stars that you could sample along as you propagate, but they would be tiny compared to what you want to explain.
All right, so the filling factor is probably not big enough for it to make a big difference. Okay, thank you very much. Yeah.
Okay, thanks, Richard. So Rostom Mubarak, please.
Hi. I have a question about the acceleration time of these of electrons at the boundary layer. So if we were to, it seems to me that it looks like it's a quite fast acceleration mechanism. So if particles, if we were to compare that with the synchrotron cooling time, it seems that for 100 microgauss or whatever, sorry, like around that ballpark, that could be like particles would have to be basically hanging out after being accelerated to 10 to the 8th Lorentz factor of 10 to the 8th. And so have you like looked into that, or what, like comparing the acceleration time to the cooling time? Like would the cooling time be lower than the acceleration time in this case, or
say again?
Would the cooling time, synchrotron cooling time, be lower than the acceleration time in this case, or how does it work exactly?
No, the
like
maximum. Okay, the maximum energy that I showed to you in the case of Centaurus A, this was dependent on indeed reaching acceleration equal to a cooling time scale at 10 to the 8. And this comes from that is in this, if you know gradual shear, you have the 1 over lambda dependence. If lambda is of the order of Kolmogorov, you have 1 over gamma to the 1/3, whereas synchrotron cooling would be 1 over gamma. So there is a regime where you kind of cross and where you reach the maximum. You need to make sure then that escape does not interfere, right? Because escape would remove the particles. So this is what the one you this is the one. This is the one I showed. Yeah. Does this explain?
Yeah, because like the Larmor radius of these particles at 100 microgauss for a relativistic plasma, I guess, should be around like 1,000th of a parsec or something like that, which is quite high. And so
1,000th of a parsec, indeed.
Yeah.
Something like
yeah.
Oh,
yeah,
no, wait. We have 10 to the 8, so we have 10 to 8, 10 to the 4, 10 to the 12, 10 to the 15, indeed, 1,000th of a parsec. This would be the class. This would be the Larmor radius, but we are talking about Kolmogorov.
Yes,
so we have a different kind of dependence. Okay.
Yeah, but if the Larmor radius is large enough for it to escape this boundary layer, it would not still keep like being accelerated through shear.
Exactly.
And so at this level, for like a 10 to the 8, that's basically what you're saying. Basically, it escapes at this at this level. Okay.
So this was the one thing I showed, right? This was going up here or saying, look, here you do time dependent. You keep the synchrotron loss term, but you ignore the escape. You go to 10 to the 8 or 10 to the 9. You get a pile up because there's balance by synchrotron and acceleration, but you don't remove the particles, right? Because there's don't escape. In principle, this will gone. This peak will look different, and as shown here, right? Because the particle will escape, you will have something here. Particles will go out. So as soon as you incorporate escape, so some which and that you have, because there is particle transport, there's spatial transport of the particle. This is what I was wanting to tell you. You have to incorporate in a consistent picture the escape. Then you will have this one, but the softening of the spectrum at the highest energy following this type.
Okay, but just to make sure, like the acceleration time of the stochastic mechanism is basically the same as the cooling time in this case for 10 to the 8 particles, or like how does the acceleration time, if you were to calculate it, like dE over
the acceleration
like
time scale is you go to this one in the gradual in the gradual shear case, you have this one, right? That you say, okay, I have a gradient in the flow, I have the 1 over lambda, and once I know everything. I have the flow profile, and once I prescribe the particle mean free path, which I assume to be Kolmogorov type, I have my scaling and I have my acceleration time scale, and then I can compare it with the cooling time scales that I assume. Now, because I told you there are many tasks ahead. So what you then assume, in principle, you could say, but the magnetic field has a radial structure as well. Okay. This will make a difference. It becomes more complex. So this assumes that the magnetic field, if you the synchrotron, right, is homogeneous along that. This would be one of the next steps to go and say, yeah. But this is what you have in your simulation, and say, well, I know what the magnetic field does, kind of, right? I know it. Therefore, I can explore the synchrotron losses. This would be a natural next approximation to that. Yes.
Yeah. Okay, thank you.
Yeah, you're welcome.
Rashmi, sorry. Hello.
Yeah, can you hear me?
Yeah.
Yeah, I had a question. Maybe it's related to Richard's question. You know, you didn't say much about flares and variability in these jets, and I was wondering if you have any thoughts on that. And I mean, it's basically with these star in jet interactions, I've heard that has been used for describing features such as short timescale variabilities. So just curious about that.
Yeah, this is a good point. But so the jet-star interaction would be related to rapid variability, and we would be thinking about parsec and sub-parsec scale jets, right? And indeed, it is a feasible example. You can figure out then what is the likelihood of probability on that scale for a star to interact, and how would it do. The best guy would be Maxim to know that this is it. But the focus here now was on large scale jets, right? Again, I would talk about a width of the 100 parsecs. I'm talking about a huge size. And there the variability indeed at the moment is an exciting proposal. So there have been, it is in the air, there's the X-ray jets, so large scale X-ray jet, which statistically show some evidence for year type variability. This is, for example, Ellie and Meyer at the moment arguing for. That has been used as another argument. I think it's not yet published, but it's been used as another argument to rule out inverse Compton X-ray origin, upscattering inverse Compton X-ray origin of the large scale jet, because the radio emitting particle would be super long cooling time scales, so you wouldn't expect any variability. What the only way then to address that in the context of large scale jet is first a geometrical effect, I suppose, that you say there may be a slight change in flow direction, Lorentz factor, or whatever, because I only need it's only at the 10% level or something like that, only minor event, or you assume that something locally happens that kind of modifies the injection in, say, for example, in a gradual shear acceleration process. But this at the moment, in my opinion, this is just vague idea and pure speculation, but realizing that something is in the air on the case of, as you mentioned, in the case of variability in large scale jets. Yeah.
But
Thank
this
you.
is, you mean this talk at the Texas Symposium, Frank?
Yes, indeed. Yes.
But there are some other developments, I mean, further developments?
Not that I'm aware of yet now. Not yet. I'm waiting for the paper.
She didn't realize how dramatic is that. So she was trying to explain in such a simple way. My feeling was she didn't realize that is something that needs.
It would have huge implications, right? But this is, yeah.
So, but yeah, maybe it's interesting to discuss about that if really will confirm this.
Yeah.
So Reshmi, do you want to conclude?
Yes, thank you, Frank. That was really excellent. Thanks for starting this session. And I just want to thank everyone for joining. And remember, we are starting this every 2 weeks. We have these talks. The next one, February 22nd, same time. The title of that is the Recurrent Nova RSO Fuki and the Galactic Cosmic Ray Connection. And Brian Reville will give us this talk. So please join and look forward to seeing everyone. Thank you, Frank.
You're welcome. Thank you very much.
Thanks, Frank. Bye.
Thanks. Bye.